Hello, so today we are going to do this problem called balance the binary search tree. And the problem says given a binary search tree, we want to return a balanced binary search tree with the same node values. So a binary search tree is balanced if and only if two subtrees, if the depth of the two subtrees of every node never differs by more than one. So if there is more than one answer, we won't want to return any of them. So binary search tree is balanced if and only if the depth of the two subtrees of every node never differ by more than one. Okay? So basically, if you have two children subtrees, the difference between their depths should be at most one. If there is more than one answer, we want to return any of them. Okay, if there are more than, if we can possibly make more than one balanced binary search tree out of the tree, then we can return any of them. And so we have this one, 1, 2, 3, 4. A balanced version of it is having 1, 2, 3, 4, and you can see the two subtrees differ by only one. And so the number of nodes in the tree is between 1 and 10 to the power of 4, and the tree node will have distinct values between 1 and 10 to the power of 5. Okay, so let's see how we can. So we have the tree node, and we want to return a node that. So what are we looking for here? So the unknown is a binary search tree with left and right children depth difference less than or equal to 1. And the data we have is just the original tree. So we know we definitely need the depth to know whether it will be a binary search tree or not, a balanced one or not. So if you take a simple example, let's take an example like this where you have two. This one is balanced already, right? But if we have something like this, it's not balanced. So to make it balanced, we just need to do something like this. So it needs to be also a binary search tree. That's something let's put that in the constraints. So it should be a binary search tree, which means in this case, we should have left smaller than root and right is bigger, right? Do we have duplicates? No, we don't have duplicates, so this is fine. So if we have this tree here, we could make it into something like this, where you have the 2 here and 3 here, and it becomes balanced that way. So what did we do here? So what we did is we took, actually this is not correct because this is not a binary search tree, right? So we need to kind of put 2 here, put 1 here. So what we did here is we did root, replace root with the root dot left, right? So and then we said that root dot right became root dot right, and then root dot left became the previous root. So kind of we did all of this. So root dot left is equal to root. Of course, these are just the values, right? So we can maybe say something like this. So we kind of swap, put this here, put this this to the left, and put this here. But the problem with this is, like, it's ideally I would like a recursive call to be done on just a left or right side in the root, right? So, but this is like done on two levels, right? I guess one thing is, we know that this, turning it into a balanced binary search tree, we could maybe traverse this one, get an array, sort it, and then use that to construct a balanced binary search tree, right? Because there is no constraint here on, like, what operations should we do. So if we have, like, let's say 1, 2, 3, 4, it's already sorted. So once we get the array, maybe we could then just start constructing a binary search tree. Well, we could start maybe by just picking the middle, and since here maybe let's take one thing that has a middle. So we take 3 as the middle one, and then we keep just constructing it like this. So so we get 2 here, and then we get 4 here, and from there we could just continue putting 1 here to the left and put 5 here to the right. And is this balanced? It is balanced, right? There is no difference between them. So I think this may work. But it's actually already sorted, right? Yeah, I think actually that could work. The converting it to a binary, to a sorted array, and then getting the sorted array by just doing, so for a binary search tree, doing a traversal where you start from the root, and so what traversal gives us, so one of the traversals, if I recall correctly, gives us a sorted array for binary search tree. So binary search tree, traversal, sorted array. Yep, so if we take, like, if we do in order traversal, which means which means we will do left, root, and then right, we will get a sorted array, right? So what we can here do first is get sorted array, or maybe just in order traversal for the node, and we need an array here. So array, what would happen is we'll need to explore the left first, so we will do in order node.left, then process the root, then we need to do in order traversal for the right node, right? And here, if not node, we should return, and here we should add the node value to the array. And so if we do that in order for the root, we should get a sorted array. And now we can construct tree from the array and then return that. Okay, so how can we construct the tree that we are looking for here? So that would be, we'll get an array, and we would have definitely a node here. So if you have a sorted array, we should definitely take the mid element, similar to binary search tree. Okay, so here we need to construct the tree from the sorted array, right? And so that shouldn't be too complicated, right? So let's try it here. Okay, so I need to construct the tree, so that would mean I will need to. So if I have a sorted array like this one here, I could just take the middle, right? So take the middle element here, and make that the root, and then recurse on this one would be the left subtree, and this one would be the right subtree, and then I could recurse on it and just do the same thing, basically taking this one as the root, the middle as the root, which I can choose to be either the floor here or this one, and then again recursing and making whatever on the left child, and whatever is on the right child. And so what I can do here is just that. So I would do mid. So actually what I would need to do here is we need a tree node here where we pass in middle element, right? And so we need to calculate that. So that would be just, maybe let me just say n is the length of the array, and we could do n divided by 2 here, and this would be the root. Let's call it node maybe. And then the left side would be the left side of the array, which would be basically construct tree here for the array left side, so without the mid element because that's the root, and then do a similar thing for the right side here. And that would be mid plus 1. And then we could just return node. And here to make sure if we have only, if n equal to 0, an empty array, we are done, right? So we should just return none. Now if it's just one element, then it's a leaf node, so we should just return. Actually, we don't need to do that because it gets handled with this. If it's just one here, let me just do maybe Python. And so if it's 1 divided by 2, it would be 0, and so we would put the first element here, so it should be fine. And so we do the in order, and then we return the node. So this should be enough, I think. So let's run it. Okay, the output looks a little bit off, but it's accepted because here we, if there is more than one answer, we can return any of them. So maybe it's good. Let's try to submit. Okay, so that passes. Yeah, so it was just essentially doing in order traversal to get a sorted array, and then from there reconstructing a balanced binary search tree using this method here.